So now, continuing our 2018 AMC 10A problems, we're on to problem 21. So which of the following describes a set of values of a for which the curves x squared plus y squared equals a squared and y equals x squared minus a in the real xy plane intersect at exactly 3 points? There's A, B, C, D, 5 options. So notice that this kind of looks like algebraic equations, so maybe we can just try to solve this. So firstly, let's just, try to graph this, because a lot of these problems with intersection can be solved using graphics. So let's just graph this. So using common sense, we know that this is a circle with radius a. So let's just draw a random circle. Its center is at the origin, okay? So its center is at the origin. So now it has a radius a. So this is a, this is a. So let's just assume a is positive, because in all of these values over here, a is positive. So let's just assume that a is just positive. So this is a, this is a, this is negative a, this is negative a. And then what's the other graph then? The other y equals x squared minus a thing. We know that y equals x squared is just this upward curve here. So y equals x squared minus a is just this upward curve that has its origin at the center moved down to having the center at negative a. So this is just the graph. Then we want to make sure that it intersects the circle at exactly 3 points like it does here. So 1, 2, 3. So one thing we know here is that no matter what a is, this graph just so as long as it's positive, so since it's positive, no matter what a is, this point is a point of intersection. It's going to intersect at least 1 point, because this graph has to have a center of negative a, so 0, negative a, and this graph has a center of 0, 0. So, and its radius is a, so it extends to negative a. So this point must be a point of intersection. So we only want to find the other 2 points of intersection and see that, and we want them to exist. So let's just try and solve this system of equations, because we kind of use what we can do for the graph. We kind of use the purpose of the graph already. We can't exactly spot a specific value for a. So let's just list out the equations and solve them. So y equals x squared minus a. Okay, so what do we do now? So let's just use substitution, because there's 3 variables, so this isn't exactly the solvable thing, but you can use substitution. So let's just say I'm going to substitute, since this is already written as y equals x squared minus a, I'm just going to substitute that into the first equation. So this is x squared plus x squared minus a squared equals a squared. So firstly, don't get scared off thinking that this will become x to the power of 4 and it's unsolvable. Just keep going and expand it, because there's no better way to do this, well, unless you want to substitute something else. But we're not going to do that now. So we have x squared plus x to the power of 4 minus 2ax squared plus a squared. But the a squareds can cancel out on both sides, so this is just equals 0. And then essentially we can factor out x squared, because that's just the logical next step, because we're kind of stuck over here. So x squared times 1 plus x squared minus 2a equals 0. So we have a factored equation. So great, because the left hand side is something factored, the right hand side is 0. So we can set both of these equal to 0 and get some results. So firstly, what if we set x squared equals 0? When x squared equals 0, x is just 0, and the graph should intersect over here, because this line is just x equals 0 line, the x equals 0 line. So as long as a is a positive value, we know that, or a is non-negative, that's something like that, we know that this point actually just exists over here. So it just exists. So there's not much of a point in solving for this, because we know that here this is just 0, negative a, so x is already equal to 0. So this is definitely true. So we want to put our focus on this equation, which is x squared minus 2a plus 1 equals 0. This is so we can basically change this into x squared equals 2a minus 1, which is pretty good, because we can just make x equals plus minus root 2a minus 1. So our two x values for these two intersections are the plus minus root 2a minus 1 things. So we want to make sure that so first thing we want to make sure that 2a minus 1 is larger than 0, or else we can't have a square root there. So 2a minus 1 is larger or equal to 0. So 2a must be larger or equal to 1. So a is larger or equal to 1/2. So let's look at the options. So this is not true. This is not true. This is, well, not true. So it's not strict enough. This might be true. This might be true. So we have to see which one fits better. Okay, so we already have 3 options out because all these have a in the range where one or more values don't fit this condition. Okay, so let's just plug in a equals 1/2 because that's one of our answer choices. Like we just plug in answer choices, okay? So if a is 1/2, let's say a is 1/2, then x is gonna be plus minus root 2 times 1/2 is 1. So 1 minus 1, which is just 0. And we already have x equals 0 here, so we have another x equals 0, which is not really helpful because we want 3 points of intersection, not 1 point of intersection. So this doesn't really work well for us. It's gonna give us 1 point of intersection, which is the 0, negative a point. So let's try a is larger than 1/2, even though we know it must be the answer choice because it's the only one left. When a is larger than 1/2, we know that 2a minus 1 is larger than 0. So x will have 2 different other values that are not 0. So x will have 3 values in total, plus positive root 2a minus 1, negative root 2a minus 1, and 0, which gives us 3 different intersection points. We plug them in to find out why. So essentially, we know that this answer choice lets us have exactly 3 intersection points. No more, no less. So thanks for watching. Bye.